heard about have been identified that are particularly extreme for being in the low redshift universe, the green peas, the blueberries, and some others. And they do share some properties with what a typical galaxy at high redshift is, with compact, strong emission lines, and low metallicities. More recent studies have analyzed that in more depth and do seem to agree that these are truly analogs of these high redshift galaxies. And of course, just 1 year ago, with the very first GECO spectra, we saw that they really look like what we have been considering analogs so far. So the idea of the talk is that studying these analogs, it's really helpful to understand and to shed light in the first billion years of the history of the universe. So the motivation for this work was to find as many and as cleanly as possible a sample of extreme emission line galaxies at low redshift that we could use later for deeper follow-up. We needed a very wide survey to get a wide volume at low redshift, because these are very rare objects at low redshift, relatively deep, deeper than what has already been observed with Sloan, and something slightly better, at least, than broadband surveys, which have already been used. Or we could see it as could it get something that would be interesting for the very high redshift community in Marseille, using a facility with only 0.2% of the budget of DWC from a city so small that it's just 0.2% of the population of Marseille. There's no riot in the city, but now there's festivity. But there's a striking difference. Anyway, this is my proposal. This is J+. It's a multi-band survey performed from a very, very small telescope, 80 centimeter, just 1,000 kilometers out from here, but covering a very wide area. The results I'm going to show are from 2,000 square degrees of the sky. We already have the data for 3,000, and a few hundred more have been observed. 7 narrow to medium band filters that you see here over this wide area to a shallow depth, let's say 20, 21, but still enough to do something. This is a precursor of the real thing that we are doing right now over there, which is J+ with 56 filters and a 2.5 meter telescope, second largest camera in the world. It's going to be great, and it's already observing. And everything we have so far, almost everything, it's public. You can get there, the images, the catalogs, everything. And there's a twin in the south as well. So first, what I did was to search for these extreme emission line galaxies, and it's really, really straightforward. We have a filter that covers the oxygen-free emission line at low redshift, so you just go there and find the galaxies that have a huge success over the continuum, which we estimated roughly with the R band. It's a bit more complicated. We got 30,000, of course, but most of them are contamination. So the good thing is that since these are really bright, you can use WISE colors and SDSS spectra that is available to try to separate the parameter space where our galaxies live and where contaminants. And in this case, you can see this very clear with the optical to infrared colors. You can see some regions with a lot of blue dots and some other with a lot of red dots. The red are high redshift quasars, the blue are low redshift galaxies. So with this simple selection, we get higher than 90% purity and completeness in this selection with 1,500 galaxies. But then to extract more information and to purify the sample, we use SIGAL to perform SED fitting with a relatively simple model. And this is an example of the SED fitting with the strong nebula emission lines, very, very nicely fitted with SIGAL. SIGAL, an interesting name, by the way, that I think I saw some potential inspiration shared, and this is a restaurant right by the harbor in Marseille. It even reminds me of the logo. But anyway, with this SIGAL fitting, we purify more of the sample, and we restricted ourselves to equivalent widths above 300, and we found 550 or so. We put the threshold to ensure completeness and so we think we get everything above that. And 400 of these were new. No one had talked about them. And well, we saw that they got low stellar masses, very young bursts of star formation, and low dust activation. In fact, when we went to check how does this compare to other previous surveys or samples collected with other studies, we saw that we were in fact finding way more extreme emission line galaxies that was thought before that were available, like 10, 20, or 50 times more than blueberries or green peas. And this is likely due to the use of a medium band filter, like almost a narrow band, because we select only what has a high flux there, a strong oxygen 3, and we don't rely that much in the broadbands. If you rely too much on the broadbands, you're biasing your selection, trying to get really extreme broadband colors, as you see here. This is the blueberry selection. You have to go very far, because otherwise you start to be contaminated by the typical SDSS galaxies. But we can go and pick only those that show the emission line. We don't care about the broadband colors. And we remove some of the selection biases like H alpha to oxygen 3 ratio. And also, well, we don't have a pre-selection, we don't have color selection like spectroscopy surveys, while being as efficient as spectroscopic or even narrowband surveys. Speaking of the spectroscopy, this is a comparison with the previous spectroscopic data that was there. And you can see a very nice one-to-one relationship in the equivalent width estimated with our data and with the spectra, also for the oxygen 3 flux, and also for the redshift, the photometric and spectroscopy. And just a couple of more things about the sample. The star formation rate, of course, is very elevated, closer, like more than 1 dex above the local relation, more similar to what has been, I think, shown this morning of very high redshift. And also in terms of the equivalent width, it also lies way above what would be expected at the low redshift, more in the realm of 1, 2, 3 redshift. But now we want to go a bit deeper. That's a very broad characterization. So I flew down to the Canary Islands to get some spectra because we wanted to be able to tell you more about this kind of galaxies. We weren't just for low resolution, but wide wavelength coverage with the IDS spectra of the Isaac Newton telescope. Very old, but very nice facility. And we confirmed that all the 30 galaxies that we pointed at were in fact extreme emission line galaxies. And we selected slightly less massive and slightly higher equivalent width than the typical galaxy in our parent sample. This is how the spectra look like, strong emission lines. We also added to the analysis that I'm going to show, I'm adding also the available SDSS spectra from before, which covered higher masses because of their selection, and a few oxygen 2. But also, less than a month ago, there was the first data release of the DESI survey, and 10 of the 400 galaxies were found there as well, so I added it to the list. The analysis was relatively straightforward. We calibrated with flux, we estimated with the Balmer-Decker and extinction, estimated the electronic density with the sulfur-to ratio, which almost always comes to the low density limit, not exactly the limit, but on that region. And then we use the direct method to determine the electron temperature, and then with that the oxygen abundance. Not for all of the galaxies, but still a decent amount. And also there's the filters. And what do we get? Well, first, I'm showing you what we had before with the blueberries and the green pea galaxies in a math metallicity plot, and also some extreme emission line galaxies from SDSS from a previous paper by a collaborator, Enrique Pérez Montero. And you can see perhaps that there's a region in this plot that is particularly empty. No, there are a few galaxies analogs for this region. What a shame it would be if the very high redshift GWC galaxies fall within that region. And oh, yeah, There are 3 of them. This is a small sample, but these are oxygen abundances determined through the dark method, so they are really, really clear. And with that area around 10 to the 8 for masses, 7.75 seems to be a normal region where the redshift about even 7 galaxies lie. Not extremely methodical, but over there. But don't worry, because we came in and we added our data, and we are kind of filling this gap. And also, of course, it covers a wider. That's one interesting point. It covers a wider parameter space, but it particularly fills that region, both the data that I took and also the results from DESI and SDSS. In fact, it's interesting because when you look at the mass metallicity population at redshift 0, we are both the JWST, our results, and the previous, at least some of the previous analogs lie below the typical redshift 0, but they don't lie so low, so much below the redshift 0 high star formation relation. This is also from the same Andrew Sammartini paper, and this is the relation that they derive in the IMA paper. So I think that's an interesting fact. We can also look at another strong line ratios that have been used as a proxy, for example, for the ionization parameter. And now I'm showing you all at the same time. You've already seen the bit by bit. And you can see that the previous analogs lie in the very high ratio area of the plot. And these data from redshift around 6, this is JWST results. These are median values. Don't lie so extremely high. I mean, we are in the high region. We've been hearing this, but perhaps in the previous analog selection, there has been some sort of analogs missing. No, some with slightly lower oxygen 3 to H beta selection due to the biases in their selection, and we are covering a wider range in mass certainly, but also in the oxygen 3 to H beta ratio. And a similar story, or even more striking, can be seen in the oxygen 3 to oxygen 2 ratio, where we do lie below the blueberry galaxies, which may have some issues with the vibration and extinction, but also below the green pea galaxies, but not so far from what has been identified with GWST samples at redshifts, relatively high rates. And also to touch on a topic that has been discussed before, the empirical equations. It is hard to measure the auroral line in large samples with JWST, so it would be great to have trustable metallicity calibrations with similar objects, but it doesn't seem to be so easy. At least this is preliminary work, but it doesn't seem so clear with our sample or with the previous ones. I mean, there's a lot of scattering, but I think there's work to be done, and it can be improved, and it's been proven, I think, hard also for the JWST community. This is a paper last year, really recent, where you can do the calibrations, but it is clearly there's a lot of scatter and there's a lot of degeneration. But still, getting a few tens or even 100 more points in these relations for similar galaxies is probably worth it. We have been doing and proposing another kind of follow-up studies, things that you can do with the very low redshift analogs that you cannot do with high redshift. And one, of course, is resolve spectroscopy done to really good resolution. We have some pilot program with the Calar Alto, and also hopefully in the coming months with the new WEAVE instrument at the Wilhelm Herschel telescope in La Palma. A few of these galaxies will be targeted with mini IFUs and very, very high spectral resolution. And also you can just straight up look at the images and analyze, for example, the individual star forming clouds, because there's a certain percentage of the sample that is not compact, and some of them are even large, relatively large galaxies, where you can identify individual clumps, analyze their properties, their masses, how do they relate with the total galaxy, etc., etc. And we have also X-ray follow-up accepted in XMM Newton to test the dependency of these X-ray flux, star emission rate, metallicity, etc. And we have more studies. We have this new data release. We can select with H alpha green P galaxies like redshift 0.3 extreme emitters, and they are proving also interesting, a bit different from the typical green Ps. We can go to the other way around and go to even lower redshift, really the nearby universe, and we still find many galaxies that have not been identified until now with the relatively strong emission lines. And yeah, I'm taking a flight on Saturday to go get more spectra on these galaxies in the sample. And as I said before, the JPAS survey is soon going to start releasing data. So this is a bit of a summary of what we've been doing with this JPLAS survey. We've compiled a very large sample of extreme emission line galaxies at low redshift, high purity, etc., which are of course young populations, low mass, little dust, high specific star formation rate. But we've also performed spectroscopic analysis and found that we can populate a gap between previous analogs identified, and that we see that they have similar masses, metallicities, and we can provide a wider range of ionization parameter that seem to be already present in JWST data. Now we're working on these other different redshift samples, and I follow up, etc. But my take-home messages are this: very low redshift analogs can be of use understanding realization era galaxies, even with JWST data, or even more important now, for calibrations and for studies that cannot be performed otherwise. And I don't know if this is a bit controversial, but probably the current samples are not full, are biased. Some kind of object we're missing. Hopefully we are filling that with more precise intermediate mass selections. And yeah, very wide multi-filter surveys, even if done with smaller telescopes, can be of use for this. And yeah, if you have any interest in anything, you can contact me, follow me on Twitter or wherever, or leave the debate. Thank you very much.
Do you have any questions?
So we limit ourselves to magnitude 20 in R-band, so the typical is 19.5 or something like that. Yeah. So Sophia, I think that's too late. Yeah. No, that's where it's 16. Yeah.
I mean, the emission line properties of these galaxies match with some very high density they will see that. What are the main differences? You want to compare this galaxy, those are very limited. They're galaxies where one has reach, or I don't know, the density of the solar.
Well, the metallicity seems similar. So if you want me to say something against my case, what I would say is the underlying older stellar population that must be because even I mean, we see mostly the only thing we see is the bright young population, but we know that at redshift 0, every time that someone has tried really hard to find an old population, they have found it in Zwicky 18, for example, or everywhere. So these older underlying stellar populations are likely different, way older, more metallic in our analogs than in those before. And maybe, but I think that might be not so important if what you're interested in is the physical state of the interstellar medium in these galaxies. What could be a bit more important is that the ratio, the mass ratio between the young and the old stellar population might be smaller in our galaxies than in the other ones. but that I think is hard to measure certainly right now from our perspective and the GECO.
Okay, thank you very much.